Yeah, let's going to start um, today's lecture. So today we'll talk about scaling law and emergent abilities. So this is a topic which has a lot of interests in the sense of how far like LLM can go. Um, so so basically, I think people all heard about people always ask whether scaling now has hit a wall or whether it has continued. For the development of LLM, especially transformer-based models, the observation is when you scale the model, the larger the better. And it seems there are new abilities coming out when you're scaling out. So this is something which basically is today's lecture. So there are some studies especially in the early days of LLMs, like 2020 or 2022. There are a lot of investigations, mostly from the industry, basically OpenAI, Google, and so on, talking about this. And later on, it's brought more awareness, and still people discuss, right, whether scaling now is still effective or not. So basically, yeah, this is a topic. We will talk about few things. This one is probably one of the early papers, the 2020 paper. It's done by OpenAI and some university. Yeah, basically they try to say scaling matters, and Chinchilla is pretty well known. This is from Google DeepMind. This scaling law is a little bit, we will talk about that. It's a complementary to the first one. It's related, but complementary. So, and we will see what they study. And I will make some comments on this as well later on. So we will explain why it's not particularly done that way. So emergent abilities, again, it's a Google DeepMind. It's try to claim that once you scale the language model, there are new abilities, they show up. And certainly there are some also counterparts of that. So we will not talk too much details, but we will just say the two views about this. And that will go a little bit very quick about the prompt engineering. We will not talk too much about that. So just the interface, because some probably needs this kind of an interface. So we are focusing on OpenAI API. So we just looking at the examples. Especially there's a new API now. So we will very quickly talk about those. But anyway, so yeah, this is I think the notebook provides some mostly on the it's not on the top three studies, which actually we did some last. Remember last time when we do the instruction tuning, there's quality, diversity, and quantity. People study that, right? So those actually is a little bit behind that, but this one is so we will revisit these ideas just to see what you study. So this is the plan. Yeah, basically, of course, when we first think about scaling law, it just says you scale the larger model, the better, right? So, but when you study that, you do a little bit more concrete investigation. Essentially, it's a kind of a predicted relationship between this model size, data size, and model performance. Model performance depends on what you really look at. Either can be downstream tasks or loss. And in the early days, like the OpenAI ones, they are looking at the loss on test data. So that's basically will it. But still, the question is how does the loss reduce when you increase model size, increase the data size? and also computation and so on. So yeah, this is a relationship actually. So when we refer to that, if you see the two papers we talk about, the first two papers, they look at this relationship. Both look at this relationship. Yeah. So basically, this is a kind of scaling law. One thing about this relationship is the following. So if you are looking at a smaller model, right, at some point you do not have the computational resource to look at a larger model. You look at smaller models. By managing these relationships, eventually you hope can extrapolate to the larger models. Either guide the design of larger models, sometimes that happens, or you just using, where you just say whether this is worth investing on. So basically this trend, assuming it goes up, then should we invest more on model size, right, data size, and so on. So this is something from a high level. I mean, people are interested because this guides you what you want to do technically. Because when you increase model size, data, they all need a lot of money, right? So a lot of resources. So this one matters in that setting. One thing, this one is not, this is the GPT-3 paper. I just put that here. This is not the scaling law paper, but the GPT-3 paper. I just want to draw one starting point, right? Starting point is it's noticed OpenAI, right? When they do the transformer from GPT-1, GPT-2, and then here is the GPT-3. They look at the trends. Basically, they see this, right? Parameter goes up. 175 is the GPT-3, so that's the model size there. When it goes up, then the performance goes up. This is one of the tables in that paper. There are many tables similar to that. This is just a translation. The higher, the better. Basically, it says they uniformly go up when you scale your model size, everything else being equal, right? So you have, yeah. So basically, yeah. Then this talk about how this scaling matters and how this will evolve, right? So should you go even larger and whatever? We know, of course, GPT-4, GPT-5 nowadays the models are larger than this 175, right? Yeah. Also, many models of that is based on MOE. We talk about that MOE in the transformer lecture. So the active could be small, but the overall model size can be much larger. So this is the scaling law. And then what we try to study, right? Basically how the law scale as power law. So in terms of the model size and data size, this is the first paper we will look at. They study this. And how do you study the generate to the other data? This one you can say a little bit about this emergent and other things. If you recall the last lecture we talked about this instruction tuning. They look at the unseen tasks, right? So it's coming from unseen data in the same task to unseen task, not even in the same task. So this kind of study. Emergent ability, we will talk about the second half of this lecture. And then there are efficiency. Efficiency is the second paper, actually. It's how do you balance model size, data size, and compute. So this is something with chinchilla law was about, okay? So anyway, so yeah, so we will, these are some of the typical topics, but you could include others. So this is this paper. I would just call this OpenAI. They starting talk about that. Certainly, even until pretty recently, people you're still talking about it, right? So basically, how do you want to scale and so on. This one is one of the first systematic studies. These are around the same time of GPT-3, right? So it's about the same time. They simultaneously come out with model, then also study the scaling law. So, basically the language model performs a predictable power law with the scale. So that's what they try to study. When you increase the size, right, and what actually the loss will be decreased according to some power law. So basically, this is. Of course, training is expensive. How should they scale model efficiently? They try to understand scientifically what the relationship so they can make a predictable decision. So yeah, these kind of questions, so that matters. At a high level, certainly this also matters. Even if you are executive in these sort of companies, you try to understand where to invest your money. So yeah, for this particular paper, they are looking at 4 quantities mainly. One is the cross entropy loss, basically negative log likelihood of this is L on the test data. And then they have a compute is one. Compute just the flops, right? Data size is another one. Database is a token, number of tokens. And the model size. Model size is a number of parameters. So basically, this is the 4 factors which are studied here, which are pretty common. If you think about what are the most the parameters you can think about, this certainly will be right. So this loss, compute, data, and the model. Compute sometimes, it's a little bit questionable because it depends on how parallelized, how you can efficiently use your GPU, right? But for simplicity, people just use flops, assuming you can fully use your GPU. Anyway, so this is about it. Here is one of the figures in the paper, which just illustrate this behavior. Basically, the behavior says the following: the loss, right? Loss as just have several other dimensions, right? Loss versus compute. The middle one is the loss versus data size. The third one is a loss versus parameters, right? So you're just looking at the loss versus the other 3 dimensions. And then you say loss decrease smoothly as a power law. So this is something which you try to see. This is in log scale, right? So this one. So this is like a line, but here this is in log scale. Just want to mention that. So yeah, that's why it's actually, if you take the log, it's linear. If you don't take a log, it's a power law. Okay. There's no abrupt saturation in studied regimes. You can continue going on, basically, right? So this is the claim. Okay, so this is the actual relationship you can look at from this table. Basically, yeah, this is this is C. Yeah, I think I should put it here. Yeah, but that's okay. So so I think I will switch this one and this one, just more aligned. But so this is basically their power law. So essentially, what the OpenAI studies is just try to understand when you increase the compute, when you increase data size, when you increase parameters, will it continue the performance relationship? The answer more or less is yes, right? So you will continue to go down based on the current. So then you can say, oh, let's scale further. So right. So this is basically a simple conclusion from that. If you don't read too much into that, but essentially there's a power law. So when you take the log in your data size or compute or parameters, this one become linear. Basically, it's a linear relation. Okay. So this is this is what it looks like. Yeah, each test vary one factors while keeping the others from being bottlenecks. So you give others try to as much as possible. Just see if even one factor matters. One data limited, increase model size each little gain. But one data is not limited, increase yeah. So basically, you want to increase both. I think there are some more to this, and the computer limited, which is both something like that. Yeah, basically they want to balance this. So this is another thing. The balance thing actually will be studied more in the second paper. They are doing much more careful about that. In the sense, they are trying to understand the optimality. They are looking at scaling law with a different emphasis. The other paper, Chinchilla, actually probably makes more of a notice, I would say, because there are some single relationship people try to talk about, which we'll come to that paper when we talk about that. Yeah, but basically, this is this is how. One thing they find which is interesting is the following, which is actually one thing I probably mentioned earlier. It's related to that similar related study, is model size matter much more than architecture design itself. So that's their conclusion. They try to look at the various. They do matter. You could do that, but the reality is they are not as much matter as the model size, basically. So this is something they try to vary to see what actually the other different model designs. You tune the hyperparameter of your transformer model, right? And you basically yeah you essentially you try to fix that the architecture what happens. The conclusion is the following. So I just read the conclusion. So performance depends on the total parameter much more strongly than to say on the parameter itself, basically. Because varying, this is absolute when you change different. So they are just different. This one is not the models are not comparable. They are more comparing the other dimensions. Okay, they are just say relative on each model size what exactly the other one will improve. And the model size you already see before, so that can make much more improvement. But here you just say very small improvement. You could gain a little bit further, but it's a relatively minor compared to what you actually do with the number of total parameters. And it does depend, but weakly. So total parameter matters, right? So when we talk about the encoder-decoder model, because you have let's say you have encoder, half decoder, depending on your ratio, you're reducing the effective model parameters on your decoder. This is a drawback of that design. So coming back to that. So increasing the parameters yields a consistent improvement across model variants. But the architecture design itself is lesser important. I'm not saying it's completely not important, but it's a second effect. Yeah. So basically, this is one conclusion, which is kind of informative in the sense of where you want to, how much you want to study this architecture design, right? So this is another thing. And basically, yeah, this is predictable as a number of counts. So I want to talk a little bit about yeah. So further. So basically, they talk about data size, right? So let's say you limit the data size when you have the parameters. This is your parameters, right? These are different data size. They try to understand that when I increase my data and increase my parameter, This actually is much more in the second paper, but essentially they started this already in this paper. They are saying, okay, when I increase data, increase the parameter, right? The question is how the performance matters. So if you look at these, so we can look at the 22, right? So this is the data size they're looking at. When you increase the parameter, they're still going up. But let's say if I have a small model, just looking at a small model, just say this one, the top one, right? Actually, maybe the middle one. Let's say so somewhere here, this guy, right? So this smaller model, first they do linear decrease, just like this guy, right? But once your parameter with data, once parameter goes up, they deviate from linear, they gradually slow down. So essentially, the larger parameters, when you have a fixed data size, the larger parameters, you have diminishing returns. Alternatively, you can see it the other way. The other way, if you have a parameter, right, when you increase data, it's a similar way, basically. Data parameter, when you just treat out one parameter versus the other one, it actually really doesn't matter as much. Basically, you have to do the both. Basically, yeah, this one you have diminishing returns unless you have more data, right? When you have more data, at this essentially it goes up, right? Eventually, yeah. Basically, this one is to do with the relationship of data and the parameter when you want to achieve the same. So this is interdependence, and both need to increase. Right. I mean, everything's pretty intuitive. You understand, but you just do a careful study about all these possibilities. Overfitting. This one is basically says when you have a model larger, right, what data, and with a certain what is essentially the degree of overfitting, basically. Yeah. So they are similar, but essentially you have to balance data, and all it says you have balanced data and the model. Overfitting depend on this. This is kind of, I mean, again, those are just empirical observations. They try to speculate from that. To scale n without a penalty, you need to increase d accordingly, because you have a huge n, it's actually starting to overfit a bit. So. On the other hand, their test loss also goes down, right? When you increase n, so the total is something different. Their training loss. Yeah, model size alone is not enough. Data scaling unlocks performance, and I think this is somewhat more to do with chinchilla. So this is something we will come back very quickly. They focus on this issue. Yeah, the later paper, and those are actually the things that turns out to be people a little bit more interested about. So that paper is a little bit more well known. They have this formula to say, oh yeah, well, what is you don't have to remember these formulas, but this just say they come out with some simple formula to say what is exactly the loss in terms of these two looks like. Compute optimal scale. Yeah. So again, this one is related to the other paper. They studied this not exactly the same way as the other paper, but they also look into, right? So compute optimal. As compute increase, optimal model size grows sublinearly. So this is they try to extrapolate when you have a novel parameter compute, right? So and then you see compute and the parameters. How does that goes? Larger model trains fewer steps, are more computational efficient. Fully convergent small model is not optimal use of compute. So basically, that's essentially what they are saying, right? So you have to balance the number of compute. Turns out this one is something in the modern way, if you look at what happens, right, most models are trained overtrained. Actually, this one will come back to the next. Maybe I will mention about the other paper when we talk about that. There are some reason for that. We'll come back to that. Overtrained in the sense you will train more than the so-called computational efficient ways, and to do that. Compute scrolling, and this is what they got basically. Yeah. So basically, the bunch of relationship. You just need to know understand what they are studying, right? What of interest and the general relationship of field. You don't have to remember, each one. Some of these. The key thing about I think would be there's a smooth decreasing of loss when you increase model and so on, and also they play around together. So I think these are just the two key concepts. Instead of something very detailed, it just draw. Actually, there are more, basically more in the paper. So which we actually, you can look at the paper as well. But I just summarize a few. So roughly that's about it. The key take-home messages, maybe yeah, just say you have to balance, right? You have to balance the data and the model. For everything increase, you get you will get some increase of your final test error, right? And then there is another thing is there will be diminishing return if you just increase one factor, let's say model or data instead of other, right? So now chinchilla. So chinchilla is it's more compute optimal. This is a part of touched in the other paper, but not studied into the detail as here. They give us some simple rule, which people seems to take because they're easy to remember, which we'll come to that rule when we talk about that. Again, it's the same motivation, right? Training large language model is very costly. You want to understand, given a fixed compute budget, what you can get out of that budget, right? With both model size and the data size, right? You have to say, this is basically coming back, this one is a compute optimal. Given C, so essentially constrained on C, the number of flops, right? You can either train a larger model with a smaller data or train a smaller model with a larger data, right? Then you want to say which one has lowest test error. So this is basically the question they are want to ask. They are doing more detailed study on this than the earlier paper, right? So basically, this is a Google DeepMind paper. And yeah, compared to that, they are more focusing on the because this first scaling law paper focusing on the in terms of loss, what is the power law relationship, right? And this one is more. They do have some computing, but this one is much more on that side. Yeah, optimal balance between the model and there's a simple relationship they give. Okay, so. The relation is slightly different than the OpenAI one, so that's another thing. And the question for fixed C, can we characterize the optimal N and D that minimizes the test loss, right? So basically, this is a question. Okay, so what it basically does? Key findings. One thing is many frontier models are under-trained. They could be even trained further. So nowadays, actually, many frontier model probably is overtrained by this criteria. We will comment on why. And the optimal, because at that time, I think it's 2022, people gradually increase the data size. I think after the ChatGPT, suddenly people pay attention to, then the data size become much larger. But at that time, it's really below 1 trillion. Nowadays, it's like 10 trillion or more tokens for the pre-train, but before that, it's just a few hundred billion is regarded a very large data. Yeah, so we need to come out with so therefore, they are looking at the relatively small data compared with model size. So that's what it says. Here is a rule, which is some people will recall this, although people never redo these experiments, right? But basically, they are rule of thumb. So how many data you need for each model size, right? From OpenAI paper, we know that you count parameters. The architecture has a less dependence, right? So you care more about number of parameters than the architecture detail. So the claim is it's a 20 times, basically per parameter 20, right? So essentially D equals 20 times your N. So this is a simple relationship, which is recommended by this paper. Yeah, so this is a law. Actually, they essentially people try to sometimes they try to talk about this law. Yeah, then increasing N is not efficient, increasing D, right? So essentially, the other one to say that is the following. If you are not undertrained, you don't want to undertrain, you can overtrain, right? If you don't want to undertrain, you should get data at least 20 size of your model. Otherwise, your data is too small with respect to your model. So yes. You could use a larger data, but it's basically overtrain side. But because nowadays people tend to overtrain. Because there are two reasons, right, tend to overtrain. When you look at all these open source, forget about the closed source ones, open source, right, they will care about at a certain model size, how much you compare with other models, right? If you are doing this, they don't even don't talk about how much compute they use, right? This is not one of the computation criteria. This is just how much better than that. So of course, then you want to overtrain that because even it's a diminishing return, it's still a return, right? So you bet. The other thing about saying that is actually overtrain is not necessarily bad idea because the compute cost here in these two papers talking about the training computational cost. It never talks about inference time computation cost. A lot of application of these models require fine-tuning and also, right, those are computational, but you have to have a good base model plus your inference cost, right? So in that case, it's good to overtrain your model compared with this. But then this one gives you a lower bound to say, oh, you should at least train 20 tokens per parameter. So this is what they try to give the recommendation of. So here is the ones here, right? So these guys, yeah. So these are the other models. They say, okay, there's some other open source models, including GPT-3. And also how many tokens they use to train this model. This one is from the paper. Later on, of course, they probably train more when they look at ChatGPT and so on, right? So, but here is something of the so-called their approach with chinchilla, right? Chinchilla. So it's here. So this is optimal. So basically, they say given a translation here, it's this is not optimal. If optimal, you have a move here, right? You move here means you need to have more token. Then basically it says it's undertrained. The model they observe from the literature based on what is reported in the literature. It's undertrained because you can, if you want to move the optimal, you need to go more tokens here. Okay, so this is yeah. For fixed compute, it's undertrained. So that's what they claim. And optimal lies along balanced curve of N and D, right? This is N, number of parameters. This is D, number of tokens. And they have this linear relationship. Yeah. A linear relationship basically is 20 times. So that's what they claim. Yeah. And increased parameter alone is not compute efficient. So basically, yeah. So yeah, so I think that's about, so you better increase the data size, right? So basically, that's all about it. So if your catch up, this is basically one sentence of summarization of what this is about. That's pretty much all it is. But we can look at a little bit other things than that. Again, as I mentioned, the current models, right? It's more here, right? It's an overtrain, right? So basically, the current model, if you look at their compute, and the reason, of course, I mentioned the reason they have to compare with other model of the same size. They have a look at the inference cost. I mean, even after the pre-train, there are a lot of post-training. They depend on that, and there are adaptation of the models. There are all reasons why you want to overtrain that instead of undertrain that. But the earlier ones is here. Okay. Yeah. So here is a rule of thumb about that, right? So basically, this is the only thing you could probably the most remembered of this formula from this. 2B, you have a 40, and 70B, you have 1.5 billion tokens, and so on, right? So certainly, GPT-3 is not using in the original NeurIPS paper, it's not trained with that size. GPT already much larger than this. It's a 175B, right? And it's smaller than that. It's sub T tokens, yeah. So basically, this is about it. For dense autoregressive regime, right? So anyway, so from scaling loss to frontier models, they are consequences. I think invest in larger models and more data. And you want to basically influence scaling decisions in later front model training. Essentially, how many tokens you want, but people, just getting more and more. So right now, frontier models shows cross domain capabilities. This one, this one is you need other data, right? It's limiting, and there are alternatives such as alignment to integrations and so on. So these are definitely investigated more recently, trying to understand. Some people say they hit the wall, some people say they don't. We do not know unless you really work in the companies to try to see exactly what is data. But gradually, people know these for certain. Nowadays, the shift already starting from the pre-training to post-training. Pre-training, the data from internet, that's more or less exhausted, right? So you don't suddenly have 10 times more data from internet. That's not feasible. So that is exhausted. But the post-training, there are a lot of things. You can generate data, you can generate whatever other things. There are a lot of investigating what tools, what other things. So basically, but still, when you in that sense, you can say, okay, you don't have enough data when you scale the model size, right? You can argue that, but it's compensated partly by the post-training, like RL, like whatever. Partly is scaling. Even you have a diminishing return, you still can scale your model. So both ways, I think it's still going on. The detailed situation, probably the Frontier Labs knows more about exactly how it's going to, because they are not publishing this anymore. But people try to question this, right? So all the people question whether the scaling law is the same as 2022, right? 2022, you see it's not saturated. Right now, it's more of a question. Anyway, so yeah, this is about this. Now we will. These are the summary about scaling law. So it's definitely of general interest, general public interest, even, right? It's simple to understand. Now we were shifting about some kind of a consequence of this scaling. This is a pretty influential paper talking about emergent abilities. Basically, they can essentially, in a single sentence, it says the following, right? A large language model, you can increase size, data size, model size, whatever. They are more looking at the model size. They say, okay, when I have a bigger model, what happens? They say suddenly something they cannot do with smaller model, suddenly it can be able to do. They have examples like COT, right? Like in-context learning and so on. They look at a few capability of a language model, then they claim this is so they can emergent abstract in the smaller model, but appear in the sufficient light. I mean, emergent now also becomes a popular word by itself. Basically, anything you cannot explain, right? You can say it's emergent. So here, this is the same thing, just say up to certain aggregation effect, emergent things happens which is unexpected before, right? So this is something you can apply to whatever you cannot explain. So you say, okay, aggregating of things but this one is also it's in general public. It's a popular topic. Emergence qualitative capability change. Something suddenly you're able to do something, and by using this scaling, right? When you up to certain level, it's a sudden change. Yeah. Sharply beyond the scale, the threshold is a sudden change. And there's a paper, we will also talk a little bit about that, because there's also discussing whether this emergent is because of evaluation metric, or it's actually just something. Their claims, at least a part of this emergent will be because of the evaluation metric. When you have a discontinuous evaluation metric, this sudden tends to be more aggressive. There are quick change. If you have smooth evaluation, like a test loss, for example, the power law of OpenAI, right? OpenAI, if you look at the power law, the test loss, there's no emergency. They're smooth power law. Emergence means they are suddenly something. It's a unsmooth jump. But the power law is certainly just one metric. They are saying if you look at some other metrics, right, certain ability, when they see certain emergency, that's because those metrics are discontinuous on the subtasks. Basically, this is what they call. So essentially, yeah, this is this is roughly the sentence. Then we'll go a little bit of detail. We don't need to go too much. Again, the high level is what we really want. Just understand this one. So emergence as a capability level observation. Scaling law describes a smooth increase in the loss. That's the first one we see, the OpenAI paper, right? So it's smooth. There's no abrupt change. But a downstream task can show this threshold-like behavior. So this is they have two common patterns. Flat and rising performance near random at small scale suddenly comes to. There's also prompt sensitivity. The paper itself also look at this kind of prompt thing, whether the ability, few shots, COT, whether they can take this kind of prompts. So essentially, for example, GPT-2 may not be able to do COT. GPT-2 may not be able to few shot learning, but the GPT-3 will be able to. So this is if you call the GPT-3 like they talks about that. So yeah, so can be looked at strong depend on whether they can. This one also regarded as abilities, right? So you can do COT is ability. You can do few shot is another ability, right? This motive is the studying of scaling using task metrics, not only cross entropy loss. And then yes, essentially, so this is complementary to the early two paper looking at entropy loss, right? This one is just looking something, and then they discover something which is interesting. So example of behavior, I just give you some examples of empirical observations across model scale, right? Few shots learning. Few shots learning basically says following. You can using context examples, in-context example, in-task learning. We actually not talking too much about prompts. So we will skip all this, but because I'm pretty assume everybody knows work with the GPT anyway, so they probably know what it is anyway, right? So that's why I choose not to talk about this. Maybe we should give some just explanation of what it is, but nevertheless, in-context learning is one, right? Chain of thoughts is another one, right? And basically, in context learning, you give few examples of what you want in your context. I think in the instruction tuning lecture, we do have some examples, right? So they have a positive example in the supernatural instruction, right? Positive example, negative example for the task description. Then the positive example you will regard as in-context examples. Then you give the language model understand what you really want based on the examples. Then they can do more, right? So basically, these two consider the capabilities. Instruction following will be certainly, but instruction following usually you could this are by tuning, code generation, and so on, right? These abilities are weak or absent in small models, but become reliable at a larger scale. Certainly, nowadays, people, although the term emergent becomes popular, but nowadays people are somewhat disputing this kind of thing because they can train small models sufficiently well. They can do quite a bit of those. Right, it's probably not as good as larger models, but good enough so that there's no emergency in this. It's not really just model small, but at that time, that's what the claim of that paper was. Right. Nowadays, it's not necessarily always true. Yeah. So. Concrete examples, right? Increases. Typical observations is small models when you have near random accuracy eventually with a few short prompts. Larger model accuracy increase very rapidly. So this is a prompt sensitivity. They give something, yeah. So about that. Yeah, this reveal capabilities, yeah, basically. So this is kind of things they actually study. So these kind of things that they study, they say, oh, I mean, this is things larger get some miracle, give you the model size, create miracles. Why does that, right? If we know the scaling law, right? So the papers, they already say that the Tesla laws is cross entropy laws. They're continuous laws, discrete, and capability behavior can change more abruptly. So this is by the other model. There are possible explanations. A larger model promote complex functions, internal representation. This is what they try to propose, right? Hubble probability on correct reasoning paths. Suddenly they are good enough so that they have more probability. There is another thing which we quickly mention is emergent may affect the threshold in the downstream evaluation rather than discontinuous in training loss, in the sense of it's just because the evaluation metric is discontinuous. There are some, yeah, this is it. So, yeah, basically, this is motivation for scale models further. Reason on it. Yeah, I think one thing certainly is related to this paper, also the other papers of the authors, this chain of thoughts, right? This certainly is something people try to put up significant investment on. Is reasoning models, right? So reasoning models, you want to increase certain abilities, which is discussed here. It's a reasoning ability. Nowadays, I think in the last year or so, reasoning model was the trend. People try to, and now they are moving even more complex, the higher level, like agentic abilities, which is usually on top of reasoning. Then you get more abilities. So you can do a lot of automatic things. Once you're starting to be able to do reasoning, then you could actually generate the things very automatically. So so now, I mean, this kind of a high level, indeed you can use much better with a higher capability models, larger models, which cost much more. Yeah, so basically, continue to improve, and there are limitations beyond the limit of compute and so on. So this is again, and this paper I think I mentioned about is the following, right? Some apparent emergent behavior may depend on the evaluation metric. So basically, that's the single sentence, essentially because it's discontinuous. So when you look at these metrics, if you measure the discontinuous, if you measure some smooth, they try to measure both and say one has a jump, one doesn't have a jump. Basically, that's the claim. So basically, this discrete matrix looks like jump. In reality, they claim it's actually not really a jump, in the sense you have a pretty smooth intermediate change, and then it causes some kind of abrupt change just by appearance. So this is their claim. So basically, they say some mirage, and they basically there's it just depends on the evaluation. Yeah, so greater change, and you can measure both, right? For example, for classification, you can measure the probability directly, right? So you can measure entropy loss, whatever, or you can measure the classification loss and so on. Yeah, suddenly in some metrics, it will have gradual. In some cases, it will be more sharp. Yeah. Yeah, so emergence can be real, but we should interpret carefully. So basically, now of that, I would say these two papers are conclusive. They just more from phenomena. Just say what is if I would try to interpret these two papers about the emergent ability versus whether it's real or not, right? You just say there seems interesting observations about sudden behavior change, and at that time, and then their explanation is because continuity. In the more modern time, as far as I know, all these small models, they are trained to certain abilities. Because the few shots already in the instruction data, right? So they are trained to do that. They could do something. If you say the COT, they are always also, again, it's trained, post-trained using that, both either using reasoning, RL, or using just instruction data. So they do have some behaviors. If you look at the coding and so on, they can also do that. So it just really the degree of there's nothing you say suddenly appear. It's really, if you say why suddenly appear, it's mostly based on data. You give them this data, they know how to do that. Instead of the model size, suddenly you can capture something which not. Yeah. So it's a modern view, although this one has interesting modern probably is it's not clear in the current landscape. There is something really emergent going on. It's more probably lack of data or lack of other things, and other things now it's also probably related to this discrete. So it's something which it's good to be aware of, but I don't think there is something which actually is you can call something suddenly emerge because of model size. You're certainly doing better and better when you increase the model size. Yeah. I think the other question probably more related to this is really, can you further scaling the model, right? For the data size, then you want to say, can you scale data, but also this one has encountered the issue about whether there's data availability, whether you can actually overcome the lack of the natural internet data, right? You have to come out data somewhere else. and that's somewhere else, how effective that can be, right? So, that will how do you want to scale? It matters rather than whether we can see some emergent abilities of these models in terms of yeah. Also, if you are focusing on training a specific ability, you just give a lot of data, then they will generally, even smaller models show some of that. Okay. If I say the what is more of a difference in the model, probably I would say the reasoning, the smaller model would tends to lack more rather than they tend to require larger models. That's general observation. Yeah, you do not do well. For example, for the larger models, you can ask them to write a plan, and then based on plan, you do something, right? So especially in the agentic setting, smaller model tends to not writing a very good plan, basically. They don't know how that, this would be one issue. Implications of scaling law. So yeah, so I think we talked a few about that, but we quickly mentioned just computation, hardware limit, environmental impact, so the data and training large model, sustain the and the data limits. So large model require increasingly larger data and data availability, and this is definitely more of a concern than the model size itself, right? Model size, you say, okay, maybe computation, but still, you can a little bit manage. But the increasing data is, I think, currently is the setting is more of a bottleneck, and try to resolve. Anybody right now, the resolve is not using the more fresh pre-training data. It's more about how do you push further your post-training stage, generating more data. You can think about reinforced learning as a way of generating more data, using model itself to generate data, and then try to evaluate. So all these tends to generalize beyond the training data, but to what extent can innovate? Yeah. So, but essentially, these are all the questions about if you want to further scale these. On the other hand, I would say concerning self-generated data, right? So we do have more use cases for this model. So like a human use that to solve some problems and can give feedbacks, and also in the agentic setting, perform tasks. Those data generated, not internet data, but those data, if you are the frontier labs, you do see quite a bit of those data. And those data certainly is a new data source, which geared towards different abilities. Those abilities can be still further developed using this kind of data, because these are really user-generated data, which has that. But what if you do, right, beyond the scaling? So what are the issues to try to address? Certainly the other issues, they are people do invest in architectures. People do invest algorithms. Also, people look at probably beyond this virtual setting, like all the LLMs working in the digital domain, physical domain, and so on. So there are a bunch of things which are do. But for all this, I think if you look at all these things, right, what is matters? I think data matters the most. Whether you can get large enough data, which of a good quality. So that's the key for all these. The question is, how do you get that, right? So. Okay, so I will quickly talk a little bit the prompts, which very high level, because I don't think we need to talk too much about in context learning. We were COT, right? I think because people use that, so they should know what it is. So we will just a little bit about the API, especially the most recent, and a little bit about the prompt, the conversational format, which is it's not a chat format. It's more about the API format. Yeah. But prompts is important. When we look at the emergent abilities, right? They at least they mentioned the two abilities considered as prompt related. One is in context learning, few shots learning. The other one is COT, right? So thinking. Thinking actually now is shifting. At that time, it was starting from prompts, but now because it's built inherent to the model, so it's starting to be more about the other lecture. But still, prompt matters. Prompt matters quite a lot, actually. It's not a lot of models are trained for specific prompts. So even you put the same prompt to say cloud or GPT, they behave differently. It may work on one, but doesn't work on the other. So actually, prompt matters quite a bit, even nowadays. People say you can remove the prompt. It's not true, because if I say cloud says that, right? But then if you give that some works well on the GPT, you realize actually it doesn't work well there. Yeah. So that's so prompt modified behavior without changing the model parameters, right? So that actually gets you additional power about model. This is actually why large language model is so powerful. It's because you can inject a lot of things into a prompt, making the behavior change. Task specification, format constraints, those are typical ways to look at that. And in context examples, these are the examples and reasoning, two instructions, especially nowadays, that's how to solve and so on. So these are related key factors. And the reasoning has a planning and so on. We will not go to those details, but yeah, but essentially, problem with prompt structure. So here we'll talk a little bit about the OpenAI message. Other are similar. OpenAI has recently changed for reason. Maybe it's a good reason or maybe it's a bad reason. But I mean, used to be we all have a system prompt. It's basically the global behavior. You do not change by if you give multiple prompts in a chat setting, right? That's usually it's a user prompt. The more systematic way, for example, you say you are a good assistant, whatever. Those are typically system prompt, just throughout the session. But now it's called the developer prompt. So instead of a system prompt. So newer, as far as I know, newer APIs, the developer is preferred, but you can still use a system if you want. The predicate pattern is something like this, right? So you first, there's a user prompt. Yeah, I think the overlay is a little bit out of order, but that's okay. So user and assistant. Assistant is GPT's response, right? So basically, essentially it's multi-turn. And put the stability in the developer and put the changing task in the user. So that's essentially user is a multi-round chat, and the developer is just across one session what you want. Append turns rather than rewriting prompts each call. So this is something like one message, right? You can take also look at the prompts dot the notebook. Notebook has more details, but I just quickly mention this is typically the message for their chat. They have two right now. They have two APIs. Chat is the traditional API, chat complete. Response is now it's more recent APIs preferred in the future because that has more control. We will see the more control. Yeah. So the basically, yeah, they say role is a developer. It's a you are consigns. Basically, it's just keep tells you where you are helpful assistant or whatever you want to put. Essentially, it's then you use say explain instruction tuning 2 sentences, right? So basically, this is user actually ask, and then you can keep asking. Keep asking. You just append each time you append. So this is something. Yeah, and what you could do, the format, right? So for exact format output. One thing nice about modern LLMs, preferred return, you can return, if you are developing a agentic program, it's not just you use the chat itself. You can ask them to JSON output, right? So this is very typical because then you can pass, or it's very easy to pass. And so on, right? 2 sentences of 3 keywords, and grounding, limit trust context, require concept from context only, reduce hallucination. So this is related to also, we didn't talk about that, but essentially the retrieval outcome generation and so on. So they try to retrieve certain context, and based on context, you do the answer. Yeah, these 2 points improves, right? So this typical using given exactly 2 sentences and so on. So these are type of results which matters. Practical look, you can have a small eval, inspect, fail, and then iterate. That's typically, turns out you need to tune. Actually, if you have a consistent, say you want to solve a math problem, or you want to do a coding, these 2 tasks are a little bit easy because all the modern LM are trained on those tasks. But let's say you're doing slightly different, maybe physics or whatever, right? So they are less trained on that. Then you have to tune your prompt to say what exactly it's doing, and then you have to do this typical loop. So structured output is something which is useful, and the modern LLMs do return. You can return this pretty well, and they are consistent with JSON format, right? Create a study plan for instruction tuning. Then you say, oh, desired output. You could just tell them desired output. Then it's a free format output. Free format output is hard to pass if you have a downstream process by another program, right? So you just say topic, steps, and estimate hours. Then but then if you say, okay, let's try to pass out by a schema which has certain properties like topic, steps, SL hours, and these are required in your output, right? And then you want to strict output this. Then you say this is a chat complete. This is older API. You can also use that with the newer API. And using this one is in the codebook, in the notebook, right? So then you say role developer, create a study plan for instruction tuning, and then this guy says, JSON schema. Then this tells you have to. You could actually tell that to return in JSON. If this is also possible, if you are saying, but then you have to put this schema into your prompts. That's another way. You can always put your schema into prompt. Just say, but this one, this revised interface make it more easier, just more cleaner, right? You don't need to talk about schema in there. They just tell the GPT, and internally they will translate that into some prompts into GPT, and the GPT will do that. Yeah, but basically, this is you can JSON. And so on. So essentially, then after you can look at the output. Output basically you have JSON have a type, have these topics, steps, and estimate hours. Yeah, I didn't list it here, but in the notebook it does have that. So you can so you are encouraged to look at that, and then you see what it looks like. Okay. Oh, actually, I do a list here. So here is basically the output. This is a JSON, this is a topic, right? And the steps, and this guy, and SM hours 8 or something. Okay, so yeah, basically, this is this is what it can give back to you. Yeah, JSON basically downstream will be easier to do, right? Schema contains enforced structure, not factual correctness. Right? So basically, yeah, it just claim that it doesn't tells you how to do that. The other one, how to do that, you have to use something like RAG or other things. Yeah. Reasoning in practice. So for reasoning, you basically you have a final answer, then you give a short rationale, right? So Yeah, I think we can get quickly, but essentially, this is the neural API. The neural API is a response. So this one is not supported by the, I don't believe it's supported by chat complete, but you can do the reasoning, right? So if you know all the modern models, they are all reasoning models. We will talk later how the reasoning is, how they're trained, right? So yeah, actually we will need to change a little bit of the last 3 lectures of these LLMs because I originally thought 2 lectures on reinforcement learning. I realized it's not possible. We have to have 3 lectures on reinforcement, then we have to skip this evaluation session. So, but the third one, we will talk a little bit about how the reasoning is trained and so on. Yeah. So the yeah, basically, this input and steps and the summary reasoning is you say immediate. They have a different. You have a low reasoning, medium reasoning, high reasoning, right? If you look at the current the GPT models, they have that. So this one just say medium, high can consume a vast amount of reasoning tokens. Suddenly you just your all the costs is going to the endless of thinking. Yeah, just. But also usually the thing is a lot of these things they tend not to try to hide these reasoning tokens from you. So you don't know what they are doing in their reasoning, but definitely they are generating something that eventually generate the answer, right? So so yeah, but essentially, you can take a look at yeah, these solve this, return this step summary, understand your so basically here is where you'll say okay, use a median reasoning of this GPT-5 mini. Okay, so basically this, yeah. GPT-5 mini is a kind of it's not that expensive. So there's even cheaper one. It's a GPT-5 Nano. So in the homework, we'll use that. The reason is we will use that to generate instruction tuning. So the next homework. The main thing is it shouldn't cost you too much, but it's good to create this kind of API, and then basically it's probably the cost I would is definitely less than $1 because the Nano is pretty cheap. Okay. But then just give you look at this and give you flavor how do you use that to generate like essentially we'll do this self-instruct, right? That paper. So yeah, but the mini is not. If you are interested, you can play. You have to get so in the whole notebook. They already have output. So if you don't want to create OpenAI keys, then you just look at the output to see what is the result. If you are interested, you can create an OpenAI key, right? API key, and then you can actually just play around with that. To use is of course in the modern setting, in the other agentic settings, they require that. Reasoning is one ability. To use is another ability. These are two the key abilities. Retrieval or calculate to external tools, something you don't have access. The LLM cannot do, right? For example, you get today's weather. LLM doesn't know what the weather is, or even not today, right? So basically, then you have to call a calendar, say today, then call a website to retrieve the weather, right? And then you answer that. The GPT does because the more recent they do have a web search tool built in. So this one example actually is web search. You can quickly see the demo is also has one web search tool, right? So basically model calls to return whatever. You can build your own tools, but then we will not talk about those. This is a little bit beyond. But here essentially is a one which is in the notebook. It says the following, right? You again using response create. Chat also can use too. Actually, they do, but then this preferred. So we will do this guy. This one is a built-in tool. It's not the tool you are provided. Find the one recent instruction tuning article, blah 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 blah, and then basically says tools is web search. So they will do a web search first, get this article. then you say, actually summarize that, tell me what it is, something like that, right? So basically they do our search, they summarize this article, and then they do. So these are 2 use, yeah. Basically, they expand the ability of, but those are all API calls. Yeah, I think we are done. Basically, you know, yeah, we are not talking too much about the prompts because we are a little bit short, right? If we could talk much more about, but then that's about it. I think, yeah, I think we were done. In summary, I will just quickly mention there's agent systems and so on, and if you are interested, so certainly, yeah. This is where the state hour comes, right? So from the 2 use agents, reasoning, and so on. Okay, thanks. So we are done for today. Yeah. Oh, how is your structure output implemented? It says, no, structure output is just the prompt. It's more from the prompts. The model is trained to be able to perform those. Internally, it's a prompt, basically. Okay? Yeah. Okay. I think that's all, yeah.